Hi, everyone. My name is Ali Langeberg, a research assistant at the Pennsylvania State University. I work primarily on the security of embedded systems and cellular devices. And to that end, I do a lot of reverse engineering and fuzzing. When I'm not hacking, I like hiking in the snow. And guess how much I enjoy the heat in Vegas now?
My name is Tianchang Yang. I'm a rising fourth-year PhD student in the same lab as Ali. Ali tackles most of the technical bits in this project. I'm more like a sales guy that's putting everything together, help him organize his ideas and his findings. Ali's hobby is just being in the wild and challenging himself. Well, my hobby is mostly just sitting by the beach and enjoying myself. And since we're currently in the middle of a desert, I feel like people need some pictures of an ocean to be in a good mood for our presentation. All right.
Before we dive in, a quick show of hands. Who here is carrying a Samsung Galaxy device? All right, and what about Google Pixel users? Nice, we've got a nice mix. And just to round it out, any iPhone users in the room? Okay, don't worry, we'll try to keep the green bubbles to a minimum. But now Galaxy and Pixel fans, you'll love to flex those cameras, right? Best low light shots, Ultra HDR, we get it. But here is the thing. Have you ever stopped wondering what's your baseband doing in the background while you are taking those perfect pictures? It's quietly parsing 5G packets from nearest tower, running millions of lines of code, and trusting every message like nothing could go wrong. Today, we'll take a peek at what happens when something does go wrong, and we show you how we made that happen on real Pixel and Galaxy devices.
Right, just for a quick background, the mobile network consists mainly of 4 components. First, you have the smartphones, or what we call user equipment, or UE for short. The base station, or RAN, which is short for radio access network, is the cell tower the UE is connected to, responsible for transmitting and receiving over-the-air signals from the UE. And the core network is like the back end of the mobile network, and they're handling things like user authentication, session management, and mobility management tasks. It also connects to the final data network to handle the data connectivity of your user devices. And to handle this communications, cellular networks uses several layers of communication protocols. For example, the RSA messages transmits messages between UE and base stations. And NAS handles the establishment of communication sessions and maintains the continuous communication with the user equipment as it moves. And finally, we have your typical data plane protocols like voice data and SMS. So our focus for this talk is mainly on NAS, or Non-Access Stratum protocol messages. So for anyone that is actually wondering, this is where the nasty in our title is coming from. And y'all had to blame Ali for that one. He insisted on having that for our title. Since these messages handle critical session management and device mobility tasks, they are critical in establishing and maintaining sessions for smartphones' connectivity. However, since these tasks are performed only after user authentication, they're typically encrypted as well as integrity protected. So this kind of added complexity makes testing this layer difficult, since only the properly protected messages are accepted. So in the following slides, we'll also cover on how we get past these checks in our testing. But due to this kind of complexity, the layer is mainly tested using over-the-air messages with previous approaches, and those are notorious for being quite slow and inefficient. So in this talk, we'll mainly use NAS as an example to showcase how we test this layer of task in the baseband and show if this kind of message function, handling function contain any vulnerabilities.
Thanks, Tiancheng. But what exactly are basebands? On top of your typical application processor running on your phone, there are separate dedicated processors running a real-time operating system. In fact, right now, there is a baseband in each of your pockets talking directly with cell towers. The baseband firmware is usually developed with memory-unsafe languages, mostly C or C++. This means that they are vulnerable to memory bugs like buffer overflows, and also they typically lack exploit protection mechanisms, such as ASLR. They're also closed-sourced, but their binary can be downloaded from online sources. All these complexities means that conversations using basebands aren't always secure. Attackers using malicious or fake base stations can exploit vulnerabilities remotely simply by sending malicious over-the-air messages. These messages might cause memory issues like buffer overflows, which can result in disrupting your connection, causing a denial of service, and also running remote code execution attacks. And even in the worst case, they can escalate attacks into your main operating system. Today in our talk, we'll focus on Samsung's Exynos baseband, but our methodology and finding can also be applied to other windows. We have also tested some baseband from MediaTek.
Right, here you can see about half a dozen of screenshots from recent talks about baseband exploitation. These aren't just simple bugs. We're talking about real impacts here, including some remote code execution, crashes, even an authentication bypass vulnerability here. And we'd like to shout out to our lab mate, who's actually sitting there, who presented that vulnerability at Black Hat last year. We want to first mention some previous works that actually helped us form the path to baseband analysis. First up is the BaseSafe. It's a fuzzing framework that targets parser functions inside basebands. It runs scientized fuzzing through emulation using the Unicorn engine. And it basically pioneers the idea of fuzzing an emulated baseband for introspection and feedback. However, as the first work of its kind, it needs a ton of manual setup for each baseband. As shown in this code snippet from BaseSafe, they require a ton of hooks setup for the emulation, which require to spend tons of time figuring out which functions to hook, and you often don't even know how many functions you have to hook until you're really deep into the analysis. Don't worry if you don't understand this code, and because actually the next work we're talking about, firmware, they're kind of automating this hooking approach by pattern matching. The firmware also brought in some full system emulation using Panda and Avatar. That means fewer manual steps and the ability to catch crashes beyond just the parsers. It also has some added nice debugging and introspection tools. But firmware also isn't perfect. They only support simpler 4G and before basebands because they only use like C code. And also, they cannot handle the statefulness of the underlying protocols running on mobile basebands. So what we mean here, if your task input doesn't really match the expected protocol state, like showing this screenshot, it just gets straight up rejected. So that makes the deeper analysis much harder. We actually circle back and look closely to this challenge later in our presentation.
And that's where our work comes in. We have developed a tool called Loris. It's an emulation environment designed for Samsung 5G Shannon basebands, but the emulation is just one part. The real power comes from its analyzer. We have integrated our emulator with Anger symbolic execution engine that lets us analyze baseband binaries symbolically and reason about their internal state. So putting it all together, Loris enables automated state-aware fuzzing of both 4G and 5G basebands. I know it sounds a lot at this moment, but don't worry about it. We're going to explain every piece of it. For now, let me show you quickly how the emulator works. You just run it with a binary, no fancy setup. It initializes the baseband, applies the necessary hooks, and then it starts the main RTOS task. From there, the rest of tasks spin up automatically. You can see their names here in green. But how did we get here? Honestly, I think the journey is more interesting than the tool itself. Building Loris wasn't just writing code. And every journey has a first step. And for us, that was figuring out where the NAS task lives. We already knew where the baseband boots from. So our goal was to emulate it until we reach the task we care about. This is a bare minimum to start fuzzing anything meaningfully. Now, this RTOS runs a ton of tasks. The good news is each task has a metadata stored in a structure, like the one shown here on the right. And this can be found from where the main task is created. Well, all these structures are stored in a global array that holds information about every task. And this gives us a solid starting point that we can scan this array and find the task we want by name. So let's take a look at task names together. Like I said, there are a lot of them. So our first move was to compare this with a 4G-only firmware to see what's new. And we found over 30 new tasks highlighted here in green. Well, you know, like LTE is for 4G, NR is the keyword for 5G. So naturally, I started with the task called NR-MTM and spent hours reverse engineering it, but found nothing that looked like NAS. So that was a dead end. Then I noticed a bunch of tasks ending in OT, and one of them, NAS OT, stood out. If you're wondering what OT means here, I don't think it really matters. Maybe auto task and some naming convention to distinguish it from other generations. But anyway, NAS OT felt like the best lead for us. And even that was tricky because the main function of this task was a decompile code from C++, and it was pretty messy. There was a lot of pointer calls, but we'll get back to that later. For now, we need to emulate until we get to the NAS task. To get there, we need to identify the CPU family of the baseband we're emulating. When Samsung introduced its first 5G phones, there was a switch from Cortex-R to Cortex-A CPUs. And this is a big change when you want to do full system emulation. The first thing, we need to figure out how the memory layout works with these CPUs, so we can load the modem code into the emulator's memory. To that end, we have to understand the address translation in a Cortex-A CPU. Unlike Cortex-R, there are no memory protection units in a Cortex-A CPU, and instead we have memory management unit. And you might wonder, well, what's the real difference? To understand that, we have to take a look at how address translation is set up with an MMU. If you're familiar with x86-64 CPUs, you might know that there is a register called CR3, and that holds the physical address of current page map level 4 table. Similarly, Cortex-A has TTBR0 to save the address of page table, and there is a specific instruction to load an address into this register. Well, we can search the whole binary for this instruction, and from there we can find out where is the address of page table. And then we can cross-reference the address of page table to figure out how actually this table is filled out. And doing that, we can find out instructions of these patterns where the upper bits of virtual address is used as an offset to the page table address to store the combination of physical address plus permissions and some attributions of that memory region. Putting it all together, we found two instances of address translation setup. First, at the very beginning of boot stage to just simply complete the boot, and it was a simple configuration. And later, a more fine-grained configuration with more careful permissions. And as you can see here, there are no RWX regions anymore. And the next step to complete the emulation is the emulation of peripherals. And this is because we are developing a full system emulator, the most important peripheral is the timers. Shannon 5G basebands are still using Shannon timer, which is already well reverse engineered by previous researchers. But I want to point out that there are more instances of this timer in the new baseband. Also, the interrupt handler that is working directly with this timer is changed from A9 to A15 MB core. Finally, there is another timer for this CPU type to work properly, and it's called Exynos multi-core timer. We also had few more peripherals to emulate, to complete the emulation and get to the point we showed you in the emulator demo. But for today, I'm not going to go into details of those.
All right, thanks, Ali. So with all of the efforts for emulation out of the way, we can finally focus on our target task, the NAS task. We first need some reverse engineering done to harness this task for further testing. Let's start with the decompiled main function first. I know this looks really daunting, but I think you guys know what these are, right? They're just some simple function calls at functions at specific addresses with different parameters. But what about this now? Like at a glance, this doesn't give you any useful information for the function call. But if you look closer, parameter 1 here is basically this pointer, which is referenced to the object in the C++. And when we dereference this, we get the pointer to the virtual table or vtable for that object. So if we now add the upside hex 10 to the vtable, we land on the fourth function pointer. And that's the actual function being called with parameter 1 and some few other arguments passed in. This is exactly how virtual methods work in C++. It is quite common in the now C++ heavy 5G basebands, but it also makes our analysis way more painful because like, who understands this math, right? And to make this actually readable, we wrote some Ghidra scripts to clean up the representation. First, we can just identify the class structures and recover their vtables. And for codes like you see here, once we know the vtable, it's pretty easy to figure out which function is actually being called. And then we also went a step further. We actually resolved the function names and put them right into the decompiled view. So how cool is that, right? With some automated scripts, we make reverse engineering C++ code so much more manageable, and we can actually get a clear function name in our decompiled code.
Now that we got some nice readable decompiled code, it's time to find actually the implementation we want to fuzz. So I turned to the greatest reverse engineering tool of all time, string searching. I searched for the known 5G NAS message names, and that led me to these strings. Of course, there was other hits too, but data IND among them stood out. From past 4G reversing, I knew that data IND is the internal message name that delivers an OTA payload from RRC layer to the NAS. So I looked at the function that uses these strings, and that way I figured out how to craft a message and send it directly to the NAS task. But that wasn't still enough. As we can see in this screenshot, sending a message to the NAS task gets rejected because this task expects protected messages. Well, like Tiancheng mentioned earlier in the talk, most NAS messages are supposed to be exchanged after the establishment of security context, which means they should be encrypted and integrity protected. Well, this is another roadblock, and we have to find a way to bypass it. Well, our first option is to find all the relevant functions, hook them, and skip them so we can do fuzzing, meaningful fuzzing. But you know that it's hard and not scalable. The other option, which worked for a while, was to use an authentication bypass vulnerability introduced in a Black Hat talk previous year. And all we needed to do is to set an invalid security header type in the input message, and that could go through all security checks. But that spark fizzled out quick, the baseband got patched, and we wanted to fuzz newer versions. And that leaves us with the third option, fake test harness. I don't know if you have noticed this in previous screenshots, but it's a pretty interesting feature or bug that when you set an item in the non-volatile memory, something like a registry, the baseband automatically skips the security checks.
So yeah, like all very cool stuff about reverse engineering and emulation. I'm sure you guys understand all the details, right? But how did we actually test the baseband? The emulation obviously is great. It gives you an ability to execute specific parts of the code, allow you to introspect which code leads to error, and gives you a lot of control and insights in the proprietary baseband. But first, let me just show you why testing in this emulation is still difficult. This screenshot shows what happens if we just send a NAS message directly to the emulated NAS task. So from the log, you can see it first received the over-the-air test message and immediately discarded that without even further processing. So if we look closer, we can see the reason for this rejection here. First, it just says that this procedure is in a null state. Represents mobility management, which is used to manage the registration, deregistration, mobility, and security between the baseband and the core network. So this is basically just saying that this thing is not being properly set up. And the second line says that the AS is also not properly initialized. AS stands for Access Stratum connection, which represents the connection between baseband with the base station. So this is saying like it cannot even find a proper connection with the base station, so it has no idea how you even receive the over-the-air message. So naturally, our testing message is discarded. And this kind of failure are expected because we're emulating only the NAS task in the baseband. So we can now run the full baseband setup. We can now do the full initialization. We don't know how its interaction with peripherals are being handled. So this kind of showcases the limitation which emulation itself cannot handle. And we commonly refer to this kind of checks as checking the states of the protocol because they capture the status of the underlying mobile protocol stage. And different state variable values will impact how the message is being handled by the baseband. The states here showing here is just only leading to some straightforward message discard, but a lot more state variables can also be lead to different message processing paths and different processing outcomes, even for the same test message. So handling them obviously is very important in our testing, but we also mentioned that there are some previous approaches that test the previous generations of baseband, so like firmware. So how do they actually handle this kind of state dependencies?
Before any sort of automation, researchers often try their ideas manually. Same goes for initializing state variables. In this screenshot from a fuzzing harness, you can see that address of state is stored in a variable, and later a proper initial value is stored in this address to initialize the state variable. In this case, the state variable is implemented simply using a primitive type, a byte. But this can be as complicated as setting up a whole structure. And it's obvious that this is not scalable, right? But to better understand the importance of automation, I've prepared a real example from baseband code. Here, you can see in this screenshots from 4G states that the EMM pros and ERC pros are accessed from using fixed offsets from their context variables on the global memory, which means they have fixed addresses. And these variables can be initialized a similar way to the previous screenshots. But we don't have that anymore in the 5G. In this screenshot from getMMState function, this function receives a pointer to facade object. From there, another object is retrieved which is called NRMM context utility, which is passed to another function, and in that function, again, another object is retrieved called general context, and finally, getMMState method from its virtual table is called by pointer. And in that method, the actual values of state variables are returned. As you might have noticed, there are no fixed global addresses here, and everything, all of these objects are created in runtime on heap. And this makes manual analysis even more painful.
Right, so obviously we need some automated ways to handle this. So to present that, let's just look at some real code. This essentially is the code leading to the log we just shown. And we reverse engineered and simplified this code from the NAS task in a Samsung baseband using Pixel phones. So keep in mind that the real code from the firmware binary is nowhere near this clean and easy to understand. And the task starts with some initialization code that enters a continuous loop to process incoming messages. The interesting bit is at line 17 and 18, where the input is rejected because the proc and AS don't satisfy the checks like we presented before. The message is only being further processed if these checks are being passed and line 19 is eventually reached. So in this toy example, there are just two state variables. In real firmware, including reaching the line 19 probably requires setting over 10 variables all to the right value. And we refer to these variables like the proc and the AS, saving state information as state variables. And so basically our task is to find what values of these state variables we should set in memory before sending some test inputs in our fuzzer so that this input can reach meaningful code regions, like for example, this line 19 where it's actually being processed. For example, we need to set the proc to be not null and AS to be in state connect for the message to be properly processed. In addition to this message being accepted, there will be also way more state variables controlling how the message is being processed and to different paths. And in total, there will be hundreds of state variables just for the NAS task. And actually, symbolic execution is kind of designed to perform such tasks. So I'll just first give a pretty simple preliminaries on how symbolic execution works for people who aren't familiar with the concept. In symbolic execution, it considers all variables as symbolic values, which means that they can represent all possible values within their range. But let's just focus on the two state variables for this example. So during its execution, when it encounters a branch, it will explore both directions of the branch. So for the symbolic execution engine knows to satisfy this first if branch, the proc variable has to be not null, versus the other direction will be that it is null. And similarly, to satisfy the second branch here, the AS variable has to be in state connect, or the other direction will be that it is not being connected. So as the symbolic execution keeps going through the code, it builds this kind of different range of variables for it to reach different regions of the code. Eventually, it will conclude that to reach line 19, both proc has to be not null and AS has to be in connect. But this here is a very simple example. It shows a very short pass. It doesn't really have those annoying nested branches. It doesn't have any for loops. We're only showing the symbolic execution of state variables instead of all variables. So we're now showing, for example, how symbolic execution is tracking how message type is assigned from message pointer. But even just for this very simplified code, like 5 lines of code, there will be 7 variables we had to treat as symbolic. Even for the code with no nested loops and only simple branches, there are 4 different paths. All of this highlight the mean limitation of symbolic execution. It is just very expensive, and the analysis space grows exponentially as the number of paths grows. So when being applied to real code, when there are hundreds of state variables and even more variables in a task, and requires, I think, a dozen of state variables just to reach the function at line 19, it just faces what we call a path explosion problem. There'll be too many variables made as symbolic, too many execution paths, and the analysis cannot even yield any meaningful result. So like a simple solution would be, what if we only make these state variables as symbolic? But that raises some additional questions. First, how do we even identify state variables? Those are not always global variables. They can be stored on the stack or heap, like Ali mentioned. They do not have any signatures we can use to identify, and we certainly don't want to manually go through the code to find hundreds of them. Well, I'm not going to answer this question here today due to time constraints, but you're welcome to find us after the talk if you want to know more. Another question is that even if we set all state variables as symbolic, is it enough for the hundreds of state variables? Well, as you might have guessed, the answer is no, because otherwise the solution would be just too simple and we don't need to go to such a build-up. By making the 100-ish state variables as symbolic in the next task, we actually tested that, and in about 4 hours of symbolic execution, it is executing over 9,000 concurrent paths at the same time. So that leads to the consumption of over 1 terabyte of memory.
Funny story. I mean, the day I was doing this experiment, one of my lab mates reached out saying, hey, Ali, I just saw the RAM usage on the server is growing really fast, and it's already 916 gigabytes. Is it normal? Of course, I didn't let him know it was me, and I just killed the process immediately.
All right, so all of that just means that you cannot really find any meaningful results before consuming all available memory. So how do we handle that? Well, please refer to our paper. I'm just kidding. I'll present that part anyways. But we are going to leave out a lot of details not presented due to time constraints, as you can see on the right-hand side. So definitely check out our paper if you're interested. We have a QR code at the end, so you guys can scan it later. But anyways, how do we really address the path explosion problem? The core idea is actually very simple. Instead of making all state variables all as symbolic at once, we start with no symbolic state variables, run the symbolic execution, analyze the really small amount of reachable code regions, but we don't just stop there. We then perform more separate runs of symbolic execution, which we gradually introduce more state variables as symbolic in each run. This allows us to uncover more code regions, and during the process, we can also reuse results from previous runs to fast-track further runs. We call this kind of iterative application of multiple runs of full symbolic execution as iterative symbolic analysis. It basically ensures that we can terminate whenever we are running out of resources for future runs, and we can use the results from previous runs for our fuzzing. I'll just present a simple demonstration of this iterative symbolic analysis to show you the core idea. Suppose we have somehow know the state variables we want to analyze are the proc and AS. In the first iteration, none of the state variables are symbolic, meaning that they will retain their original concrete value. But we had to make the message pointer as symbolic, since this will be our input text message. So we want to find out all of the paths reachable by different values of this input message. So in the first iteration, only message pointer is symbolic. Then we symbolically executing, maybe from the start of this function. Suppose we have somehow and then we reach line 16, where we encounter the first branch depending on message type. Since message type is assigned from message pointer, we can get past this branch, no problem. But at line 17, we encounter the branch depending on a state variable. But in this iteration, the proc is now symbolic, and its default value will be that it is null, so it cannot satisfy the branch. So we have to stop here, and we can now reach the target line 19. Then in the second iteration, we start again from the beginning. Since last time the value of proc is what we given the problem, we make it as symbolic in this run. We can reuse the results from previous run and fast track to line 17. Then now the property variable is symbolic. We can analyze this value to satisfy the branch, which that it is not null. And we can keep executing. At line 18, we encounter another branch depending on our non-symbolic AS variable that we cannot satisfy. So we had to stop here and then go back from the beginning in iteration 3. And at this time, we make AS as symbolic. And fast track to line 18, where we can find the condition for it to satisfy the branch, which that it is in connect. And this will allow us to eventually reach our target line 19 and collect the required condition.
Well, let's summarize Loris before we talk vulnerabilities. We start with the firmware binary, and then we have our emulator built on top of firmware. We have extended firmware to add support for 5G Shannon basebands. At the core, we have our iterative symbolic analysis, which Tiancheng explained about it. And on the fuzzing side, we have a grammar-aware fuzzer, which automatically generates NAS messages. Tiancheng will tell you more about the fuzzer.
We integrate a libafr-based fuzzer, and we will choose the state variables and values we want to use. And we will initialize the emulated NAS task with these variables and values. Then we will send the test inputs through the initialized emulation. We tested both the 4G task and 5G NAS LTE task for the commercial baseband, from phones including Samsung Galaxy S21 and Google Pixel 6. So after running fuzzing, we actually discovered 7 unique crashes, all of which are exploitable using over-the-air message on real phones. Those are all previously unknown, and those include 1 critical vulnerability, 2 high, 3 moderate, and 1 low assignments from vendors. We also found additional 1 heap overflow bug that is not one of these 7 real crashes. We found it during fuzzing, but we cannot really reproduce it when testing with the real device. So we eventually found that because this requires sending a really long payload to the NAS task, but the payload is actually discarded by one of the lower layers, so it is not delivered to the NAS task. Samsung also said that this is a bug, but it will not lead to any real exploits. And because we're doing kind of isolated NAS task testing, this kind of showcases our limitation of potential false positives. So maybe future work can address this that exists in our testing. But still, 7 exploitable crashes are great. We got 5 CVEs assigned for all of the moderate and above vulnerabilities so far. And to validate them, we replayed this crashing fuzz inputs and send them over the air to real devices. We did this using a USRP B210 with OpenAir interface as the base station and Open5GS as the core network. And for every exploitable bug, the baseband just crashed immediately. So let's take a look at the baseband crash in action on a Samsung Galaxy S21. To enable debugging, we also toggled on Samsung's upload mode, which upon baseband crashes, the phone automatically reboots and enters a debug mode. Without this mode on, the phone will simply lose its signal and require a restart or toggling the airplane mode off and on to recover. So after, you can see here we disable the airplane mode. The phone just starts the registration procedure with the network setup. And during this procedure, the phone receives a malicious registration accept message, which causes the baseband to crash. So the phone mirror here just disconnects. But on this other camera, you can see the phone is kind of rebooting, given a minute. And it goes straight into the upload debug mode. And on the left-hand side, you can see the details of our attack over-the-air messages.
So does these...
Thank you.
Does these bugs just crash the baseband? Not quite. As we mentioned, we found both stack and heap overflows. Now, to turn a stack overflow into a remote code execution, you typically need an RWX stack. So you can inject the shell code and run it. This means the execute never bit has to be off. Also, you need to find a way to get around stack protections, like canaries. And some basebands, those protections are weak or even missing. On the other hand, heap overflows can also lead to RCE, though the payload size might be limited. Still, a write what were primitive is a better gain from a heap bug, and that can give us more control and more powerful exploitation options. And if you remember from the memory layout slide, I mentioned that the 5G baseband don't give you any RWX region anymore. So the next question is, how good are their stack protections? Let's talk about that. To keep everything organized, functions use stack frames. Let's take a closer look at the stack frame 2. At the very bottom, we have return address stored from link register. And on top of that, we have local variables of this function. Right on top of return address, the stack canary lives. And that makes sense because it's supposed to protect the return address on a stack. Let's look at an example from baseband code. In this function, at the very beginning, the value of canary is loaded from a global address and stored on the stack. And then we have the function body, which here simply calls another function. And at the end, value of canary on a stack is compared to the original value of canary on the global memory. And if they match, it returns normally. Otherwise, it calls check function, which aborts. Well, and if we jump to this address, we'll see a fun hexaspeak cipher code. Very dramatic, right? But don't be fooled. It's not always this value. The canary gets randomized on every boot. But here is the catch. It lives in a memory page with write access. So this can give us a potential path to bypass it. Like I mentioned earlier, a heap overflow can give you a clean write whatever primitive. And this is well covered in a Black Hat talk from 2 years ago. But in their talk, getting an RCE needs an RWX region. Now, if you can't inject code to exploit a baseband, you can still use the existing code to run something malicious. And that's where return-oriented programming comes in. Well, an attacker could use the heap bug to achieve a write whatever primitive and bypass stack canaries by overwriting the original value on the global memory without crashing baseband. And later can chain it with a stack overflow with some ROP gadgets. So, for example, that can lead us flipping the NRMM fake test enable flag in the NVRAM. So the baseband would start accepting all messages in plain text.
Yeah, just to be clear, we really don't have time to go through the whole remote code execution, but we know that those are possible. We have the real heap overflows and stack overflows that are accepted by the vendors, so we know that it's possible. With all of our techniques, we can basically uncover baseband code, more baseband code in our testing. Here, as you can see here, the top lines are basically what low risk covers in its testing, and bottom lines are the previous approaches, including what firmware can cover in its testing. With the automated way that low risk tests, we can basically achieve even more than double the coverage of previous approaches. They also require a lot of manual efforts to set the baseband to correct states, and that require like hours of work even for people who are familiar with the baseband. So the bottom line is like we are more efficient and we can cover way more code with just automated testing.
Well, for many reasons, baseband are getting more complicated every day. This is due to new generations of cellular protocols emerging because of new functionalities added with firmware updates and also new hardware introduced with, every year with a new phone model. But this doesn't mean we are helpless. If we spend time to understand firmware internals, we can still build automated and smarter tools, and that can lead us with better results. And just to be clear, complexity doesn't mean better security. In fact, it often hides vulnerabilities even deeper. So there is still a lot of work ahead. We need more research, more tooling, and definitely more focus on the protocols that we haven't been able to look at yet. That's all from us. Thanks for listening. Big thanks to our collaborators and Samsung and Google for working with us during the disclosures. You can check out the paper and code using these QR codes. And if you have any questions or want to chat more, feel free to reach out.